the first time you see that, part of you wants to kind of like think, hold on, that's ridiculous. But if you actually think about it a bit longer, you might be kind of terrified by that prospect and think that's actually something that's very disturbing. Let me really think about it.
There's only 10,000 of you in the world right now.
Professional astronomers.
Wow.
Yeah, professional. JWST is like a time machine. You're looking at light which has traveled for billions of years to reach your eye. I myself am using it in October, which I'm very excited about. It's kind of ridiculous to say out loud, but an interstellar propulsion system that we're designing in my team. I think he's put in $100 million of his own money so far into this. So he's serious. I mean, this is the biggest investment I've ever seen in something like this. It's much harder to live on Mars than it is Antarctica, put it like that, right? Antarctica has an atmosphere that we can breathe.
Do you think man landed on the moon?
We actually bounce lasers off the surface of the moon, off these mirrors, and before you know it, you get an infinite number of these particles collected between the two wormholes. The instant you form the two wormholes, they immediately collapse due to this effect. It will be like a nano chip, like a tiny, tiny spacecraft that will weigh like just 1 gram. It'll be stretched out into a tiny thin sail, and this very thin sail will be pushed by a laser beam.
I don't know what's in, maybe they put shrooms in this tea. Maybe there's ayahuasca. Rob, what'd you put in this tea, Rob? Did you put something in there?
I want to do whatever I can in my life to try to advance humanity's mission to try and achieve that. I think I'm not going to solve it, I'm one person, but maybe I can add a small piece to the puzzle and we'll get there together.
Did you ever think you would make it? I feel I'm so close I could taste sweet victory. I know this life meant for me. Yeah, why would you bet on Goliath when we got bet David? Valuetainment, giving value's contagious. This world of entrepreneurs, we get no value to haters. How they run, homie, look what I become. I'm the one.
I told David when he walked in, I said, David, I'm about to have a workout. My brain's going to have a workout today because we're sitting down. Anytime you sit down with these astrophysicists, you just have to know your brain is going to go all over the place. And every time afterwards, I feel my brain, I feel swole. It's like the muscles coming out, it gets cut up. So that's the goal today. David Kipping, prominent astrophysicist, known for his significant contributions to the study of exoplanets and the development and innovative techniques in astronomy. He's held positions at institutions such as Harvard University, Columbia University, where he continues to advance the field of astrophysics. And you also have a YouTube channel as well,
That's right. The Cool World's YouTube channel. Yeah.
Which I love. I mean, some of the stuff, you sit there, you're going through the whole thing. You get millions of views with your content as well. We'll put the link as well below for people to go through it. But I got a bunch of questions I wrote down. Okay. Yeah, random questions for my own self. Okay.
They're the best.
You know, some of the stuff that, it may seem innocent to you. Some of the stuff that may be like, why is he asking me a question like that? Who cares about that? But regardless, they're important to me.
Right.
Okay.
Let's do it.
And let's see what this is going to turn into. Okay. So a story comes out recently talking about Earth's rotating in reverse direction. I don't know if you saw that or not. I'm sure you have. So scientists have confirmed that the Earth's inner core, Rob, if you want to pull up the story, has started to rotate in reverse direction. According to a research study published in Nature, scientific community has been struggling to confirm the phenomenon for years, but the new evidence supports a 2023 hypothesis about the inner core's rotation rate. Now, some are saying, man, you got to be careful with this because this is the end of time. This is this is that. What does it really mean when the Earth's core is now starting to rotate in reverse?
Look, I think with this story, it got a little bit misrepresented.
Okay.
So first off, full disclosure, I'm an astronomer. I do not study the insides of the Earth. I'm not a geologist. I took, when I was at college, I took geology. So that's one of the subjects I studied. But this is a story which I think, from the outside, seems to be misrepresented. So my understanding of what's actually happened is that there are inner layers of the Earth which are rotating. And imagine that there's two layers and they're rotating in the same direction, but one's going faster than the other one. And then what's happened is, even though they're both going in the same direction, the inner one or the outer one is now going faster than the other one. So they're both still rotating in the same sense. It's just that the relative motion as to which one's going faster has changed. That's what's flipped. So it's a reversal in the differential speed between them, but not the absolute speed. So they actually are still going in the same direction. But of course, that doesn't make a very snappy headline. So I think a lot of the confusion was people misrepresenting this story a little bit and seeing it as though it really was like the inside was completely flipped over.
So this inner core intrigued researchers since its discovery of Danish seismologist Inge Lehmann in 1936, and how it moves, its rotation, speed, and direction has been at the center of a decades-long debate. A growing body of evidence suggests the core spin has changed dramatically in recent years, but scientists have remained divided over what exactly is happening and what it means. Part of the trouble is that Earth's deep interior is impossible to observe or sample directly. So what is the risk? Based on just what you know about, you're an astrophysicist, not a geologist, but what is the risk if it does go the other way? What do we know if it does do it? Like, what's the big deal if it does?
I think the risk for us is probably the magnetic field is a big obvious risk. So, we are bombarded by cosmic rays, high energy radiation from space, and that's striking the surface. If you're underneath the ocean, you're dwelling in the ocean, you're deep underground, you're probably fine. You're not going to be affected by this cosmic radiation. But if you're on the surface and we suddenly lose that magnetic field, that's what gives us like Aurora Borealis, the northern lights. Without that, we're going to be exposed to far higher levels of radiation. And so this is thought to be potentially a crucial criteria for looking for planets which could have life on them. We want them to have strong magnetic fields. If the Earth's magnetic field, and we actually do think over millions and millions of years, it does flip. So the North and the South Pole do flip periodically. We see that in the geological record. I remember learning that at college when I was studying geology. You see these magnetic lines on the sea floor which kind of strip over. So the magnetism of the surface, as you look at different layers of the ocean bed, have actually flipped in their magnetic behavior. So we know the Earth's magnetic field does flip. The question is, how fast does that flip happen? Does it happen like overnight? And so you go to bed at night and you got a strong magnetic field, and while you're asleep, suddenly the field switches off, but it goes back to normal just the other direction, fine. Or does it stay off for tens, thousands of years, which would be very bad? That could actually severely impact life on the surface, including us. We just don't know, but it is likely that it will flip again in the future. But
it's not a crisis if it does.
It depends. We don't really know. We've never sat through one. So, we've got this geological record, but that's so granular. It's not giving you that fine detail.
How did they even find out, by the way? How do they know that's happening?
So they know this from looking at when you look at the ocean bed, there's these layers of material, sediment, which fall onto the bottom of the bed. And that's basically like a time capsule. So if you dig deep down, you're seeing a layer which corresponds to hundreds of millions of years ago. And you can measure the magnetism of that layer, and you see that it is flipped compared to the next layer and the next layer. And it's going opposite and opposite and opposite. So from that flipping, you can tell basically from the thickness of these sediment layers, roughly how long the Earth's magnetic field is flipping. So I don't remember the exact number, but sort of millions of years or so, you see this flipping happen. So it is inevitable, I think, that the magnetic field will flip. And we certainly think when we talk about astrobiology and the search for life in the universe, that having magnetic field should be a really important criteria for life. So I certainly hope, and I think you should hope as well, it doesn't happen in our lifetime, because it could be a bad day.
Yeah, that makes sense. So obviously, we will be praying for that not to happen.
Yeah.
Based on it could be a confusing time.
Me too.
But for a guy like you, astrophysicist, somebody who goes to school and you're studying this topic, right? One, what makes you study a topic like this? Like, since you were a kid, was this something where you were fascinated with it?
Yeah.
And then two, now that you have, and you're in it, and you've read all these papers, you've written papers, you've been around the community, what's keeping an astrophysicist up at night?
Well, I was always fascinated by the universe, I have to say. So ever since I was like 5, 6 years old, about the same age as my son, we were just talking about as we came on, he's got the same kind of bug as me. Like he just has all these questions about the universe and space and everything really, but especially astronomy. And so I was like that. And I remember getting this book that my parents bought me, and it was an annual of the planets, and it had, a page all about Jupiter and all of its moons, and then Saturn with its amazing rings, and it had even more moons, and the size and masses of these things was just mind-blowing. I just couldn't believe what was out there and how large and vast the universe was. So I really caught the bug. I got into science fiction a lot when I was a teenager. I was watching all the Star Wars, Star Trek stuff, loved all that kind of stuff. And then when I was at high school, I remember my high school teacher said to me, you know what, you should, here's some physics books. I would, maybe look into particle physics and quantum physics and stuff like this. So I started to read books on that. I got hooked into that world. I kind of left astronomy, did my degree in physics. And then towards the end of my degree in physics, I came back to astronomy because there's so much left to discover. I think in physics, we often get the feeling, at least I had as a student, that to make progress at this point, requires billions and billions of dollars. It requires huge teams, hundreds, thousands of people. And you will be, accredited down there as like the 5,000th person who contributes to this. And some people get a kick from that, but I'm more, maybe entrepreneurial, and I like doing things by myself and driving something forward. In astronomy, you're never going to run out of stuff to discover. There's 100 billion stars just in our own Milky Way. There's only 10,000 astronomers on planet Earth. So each of us has millions of possible star systems that we personally could just have as our own star systems to
There's
study.
only 10,000 of you in the world right now.
Professional astronomers.
Wow.
Yeah, professional.
Interesting.
Yeah.
And is there a community where you guys all get together? Like, is there the annual convention when everybody gets together and meets each other, or no?
Yeah, there's a few different organizations like the International Astronomical Union, IAU. That's the organization which famously demoted Pluto. And that's probably its most famous thing that it ever did. And people still have a lot of hard feelings about that. And then there's also the American Astronomical Society, the AAS. And that has about 3,000, 4,000 astronomers who regularly attend that meeting. And so I'll probably be there in January. There'll be a meeting.
What do you guys do when you guys are together?
We just hang out and nerd out about space. Is
that literally what it is?
No, we just geek out. Yeah, we bring our lightsabers. No. I wish. No, we share our results. We're like, here's the latest cool thing that we've been working on. There's just it's like kind of exhausting. It's a series of 5-minute talks, 5 minutes, 5 minutes. And you get just bombarded with all these new discoveries. And then you just on the plane home, you're like, whoa, like all this new stuff that I've just learned and discovered. What am I going to spend the next year working on? This is like amazing, all this stuff happening, but it's a lot to digest. There are so many people working
Is it more coming from a place of, oh my God, this is so awesome. I got so much more to learn. Does it ever get to, whoa, if that actually happens, that's pretty bad. And let me find out a little bit more about this. Which one is it? Is it more the childlike excitement to learn? Or does it ever get to a point of, this just got serious?
A bit of both. I mean, yeah, sometimes you'll hear a talk that will kind of scare you. I mean, especially if it's about the politics or the financial situation in astronomy or something like that, because we'll have those talks at these meetings as well. There'll be people talking about the NASA budget or the cost overruns of missions, and that can be pretty scary, quite frankly, because our careers and progress is ultimately linked to the funding to these organizations. Other times it's something kind of terrifying or thought-provoking. You've had Avi on the channel before, Avi Loeb, and he's been talking about how Oumuamua, this interstellar asteroid, or at least we assumed it was an interstellar asteroid, he was saying, well, maybe it's something else. Maybe it's actually an alien spacecraft. And look, the first time you see that, part of you wants to kind of like think, hold on, that's ridiculous. But if you actually think about it a bit longer, you might be kind of terrified by that prospect and think that's actually something that's very disturbing. Let me really think about it. And I think we owe it to people like Avi, as controversial as that idea has been, to give it due process and due thought. And when we have these new ideas, they shake things up and they force us to move forward. So yeah, those are actually kind of the most interesting talks.
So at this point, I was looking up what percentage of the universe hasn't been explored and, what we don't know about. You'll see the number 95%. We only know 5%, right? And in the ocean, they'll say 94%, we don't know, 6% we know. So those two numbers are relatively around the same thing, right? So if we don't know 95% of it, we only know 5% of it. Yeah, can you zoom in on that? We only know 5% of the universe. Remaining 95% is still a mystery, an unknown universe of new particles and force of waste discovery. Okay, if that's the case, where are you at with, if there's another, living aliens out there? How do you process that? Are you more from the community of saying, no, I don't think there's anything there. I think it's just what people want. They want that to exist because it's exciting, it's exhilarating. That means all these movies, Alien, E.T. Phone Home, these things are real. Guys like this exist. Or you're like, nah, I hate to kind of be the bearer of bad news. There's really nothing like that out there.
Well,
where do you stand?
Let's just say first thing about this number, this 5% number or 4% number here. So that's actually talking about the fraction of normal matter in the universe, what we call baryonic matter. So that's the same kind of things that Desk's made out of, you and me are made out of, protons, neutrons, atoms, electrons, things like that. But the other 95% is dark matter and dark energy. So that's what it means by that statement. But even that's not true, because we don't know about 5% of even all the normal matter, the vast majority of normal matter is so far away from us.
You're saying even less than 5%.
Oh, a minuscule. I mean, what do I know about a star that's on the other side of the Milky Way? Nothing. We don't even know about its existence, quite frankly. A star on the other side of the Milky Way is undetectable to our telescopes. So we know about only really the stars which are in our local neighborhood, maybe about of order of 100 million to a billion of them. There's at least 100 billion stars around the Milky Way, and there's 100 billion galaxies outside of the Milky Way, of which we know hardly anything about their microscopic, in terms of the stars and the planets, that kind of properties. So, I don't know how you put a percentage on that, but we know next a fraction of a fraction of a fraction of that number, I'm sure. And then, coming back to this, what could be out there, in terms of life and aliens and this kind of thing, look, that's the reason I got into astronomy. I was fascinated by that question. And, I said, I was watching Star Wars, Star Trek, and I would look up at the stars thinking about that question, wondering if there was someone out there who would hopefully fly by in a spaceship and beam me up and show me the stars in the universe. That was my dream. So I've always hoped that there was life out there. But as a scientist, my job is to decouple and divorce my wishes and desires away from objective truth. My job as a scientist is to seek objective truth, not what I want to be true, but what is actually true. And that's pretty much the only game in town which does that in terms of a human endeavor that we actively participate in. And so I think that's beautiful, but it does require a lot of conscious effort to, hey, what do I want to be true? If I want that to be true, I should probably be pretty skeptical about any time I see something where I think that. If I see a UFO and I really want that to be aliens because it would just be so cool and so interesting if that was true, because I want that to be true, as a scientist, I have to be extra skeptical of that possibility. And so that's where your skepticism and the skeptical brain of a scientist really kicks in. So I try to be just agnostic. Let's get data, let's collect the evidence, and when the evidence becomes compelling, overwhelming, then we'll go for it. But we certainly don't have that evidence at this point.
We don't have that evidence at that. So you're saying, you don't believe there's aliens out there. You're not a person that believes.
I neither believe nor don't believe. It's just I want to do the experiment.
You want to know or not know. That's what you want to know.
Yeah.
Okay. Have you? How much research have you done? Speaking of people who claim they've seen, have you spoken to others who have? And when you have, what do you ask them?
I've spoken to people, not in my podcast or the channel, but many individuals you meet in life. I remember my high school teacher told me that. I went back to my old high school and he told me a story of when he saw a UFO. I've had my sister and sister's fiance at one point was telling me stories of UFOs he'd seen. So I've had many people, because I'm an astronomer, they think maybe I'll be able to debunk this or explain what's going on. But I can't. I mean, you can't take a first-hand story like that and explain it. It's just not enough information. I mean, I don't have any equipment to observe or go back. So
out of your 10,000 peers who are other astrophysicists or astronomers, out of the small community you're part of, what percentage of them are convinced there are UFOs out there?
I think it's small. I've never done that poll, but I think the idea
less than 10 points.
Let's put it this way. I think the idea that UFOs are aliens, I think would be small. I think the idea that there are unidentified things in the atmosphere would probably be quite high.
Living.
I don't think that'd be high. But it depends what you mean. If it's a drone, is a drone living? If it's a Chinese drone,
no,
do we
that's
count
not
that?
living. Nope.
Yeah. So I think if you're thinking about something that's truly extraterrestrial, I think the fraction is quite small. That people believe that what we are seeing is truly evidence of aliens.
Is there another planet that's very close to Earth, kind of like us, where there could be a civilization?
Yeah, I mean, the closest star system to us, Proxima Centauri, actually has a fairly Earth-like planet around it. We don't know quite how Earth-like it is, but it's called Proxima b. Proxima Centauri b is the name of the planet. It's only a little bit larger than the Earth, and it's in the right distance away from its star that it could have liquid water on its surface. But that's about all we know about it. We just know basically its size and how far away it is. And
how do you get there? What's the freeway exit on this? Is there?
This is 4.2 light years away.
Yes, that's a long ways route. That's not Delta Airlines or United.
There is an attempt to go there. So there's a project by Yuri Milner, who's a Russian billionaire. He lives in Silicon Valley now, and he's actually trying to get all the tech gurus in Silicon Valley together and scientists together to try and fund a mission called Breakthrough Starshot. I think he's put in $100 million of his own money so far into this. So he's serious. I mean, this is the biggest investment I've ever seen in something like this.
Comparable to the moon. How far is this comparable to the moon?
The moon is a few light seconds away. I think like 2 light seconds away, something like that. And this is 4 light years away. So it's 4 years divided by 2 seconds. So far, 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 far further away. Yeah.
Far further away.
Yeah. I mean, with this mission, they want to travel at 20% the speed of light, which is totally unprecedented. With nothing, if you took the fastest thing so far, that's the Voyager 2 spacecraft, it would take Voyager 2 about 10,000 years at its current speed to get there. They want to get there in 20 years, right? So that's a huge speed up, a factor of 500 speed up. So to do that, you can't have a vehicle like a conventional space shuttle or a spacecraft that someone would sit inside. It will be like a nano chip, like a tiny, tiny spacecraft that will weigh like just 1 gram. It'll be stretched out into a tiny thin sail. There will be just maybe 20 or 50 atoms across, incredibly thin. And this very thin sail will be pushed by a laser beam. Now, light has pressure. We don't notice it, but this light shining in my face, it's actually slightly pushing me back at a very, very minute force. But I'm so heavy, it's not enough to move me. But if you make a very, very light, thin sail that's highly reflective, it can be pushed. So they're going to bombard that with a massive laser, gigawatt laser from the ground that will accelerate it to speeds approaching the speed of light, ideally, and then get it to fly past Proxima Centauri. It won't be able to stop there. It will just go straight past and hopefully just snap a couple of photos and then somehow, the question is how, beam that data back to the Earth so we'll have the first ever true photo of another world.
So this is not a person or group of people, as that are going to live in a whatever spaceship for 20 years to go there, see what it looks like, and either stay or come back. That's not the case.
We wish we could do that, but no one really knows how on earth you would do that. That's just complete science fiction. We don't have any propulsion system that could possibly get humanity to another star system in our lifetime.
Okay, so as of right now, how much do we know about this? What's it called? Yeah, what is it?
B.
I want to say the name right. Proxima Centauri B. How much do we know about it?
Precious little. It is around a very strange star, but also a very common star. So the star is actually the most common type of star in the universe. Is called an M dwarf, and this is what this star is. It's in a triple star system called the Alpha Centauri system. There's Alpha Centauri A and B, which are pretty close to each other. I think they're sort of the orbit of Jupiter around the sun away from each other. And then there's Proxima, which is really far out on a very wide orbit around this binary star system. And then this little star, it's very diminutive. It's about, I think, 1/8 the mass of the sun, so a very small star. You can't really make stars that much smaller than this, else they wouldn't even be stars anymore. They'd be failed stars. So it's one of the smallest stars you can have. And around this very dim red star, we find this little planet, Proxima Centauri B. We think there's actually additional planets in this system. There's probably a planet, we call the first planet that was discovered Planet B, and then we go up the alphabets. The next one's C and D, and I think there's evidence for a C and a D at this point. Astronomers are still arguing about the reality of those two, but it looks like a multi-planet system with an Earth-like planet in the habitable zone, and that's about as much as we know. We don't know much about its atmosphere. We don't know about its surface. We certainly don't know about life on it. People have searched for radio signatures. They've beamed our most powerful radio telescopes and listened. Do we hear a communication? We don't see anything. It's completely silent as far as we can tell. So as far as we can tell, it's just another Earth. And probably there are a lot of Earth rocks out there. These stars, we have worries about them as being possible habitats for life, even though 3/4 of all stars in the universe are like this type of star, these red dwarfs.
3/4.
Most stars in the universe are like this guy. We're the freaks of the universe living around a sun-like star. I always think that's wild. People don't realize that. Like we live around a single star system, not a binary star system. That's already kind of odd. About half of all stars are in binary star systems. And then on top of that, we live around a yellow star, sun-like star. Only about 10% of all stars look like our own sun. And the other 75% of them, there's a big bracket below that, which look like these guys, these M-dwarf stars. These stars are amazing. They live for trillions of years. Our sun's on the way out, only has about 1 billion years left, and then the Earth will be uninhabitable. Whatever we do with climate change, whatever we do to the planet.
How much do we have left?
Less than 1 billion years.
We have less than 1 billion years.
Yeah, so the sun will not engulf us at that point. I think people normally think the sun's going to gobble up the Earth. That won't happen for about 5 billion years. But way before that, the sun is increasing in power. So its luminosity is growing gradually over time. It's already increased by 30% in the last 4 billion years. So it's already been growing in power significantly. If it gets much more powerful than it currently is, it'll tip us out of the habitable zone altogether, irrespective of what we do on this planet, human beings. So even if humans are long gone, Earth will still be pushed out of the habitable zone in about 1 billion years. So when that happens, maybe Mars might become habitable for a short while as the sun continues to warm. But it really is kind of an endpoint, you might think, to life in this solar system. Whereas these stars, these M-dwarf stars, they can go for trillions of years. That's far older than the current age of the universe. And so I think it's a mystery. I call this the red sky paradox. How come we don't live around one of these stars? There's more of them. They seem to have more Earths around them, as far as we can tell, than sun-like stars, and they live far, far longer. So that seems like they've got everything going for them. And therefore, it's kind of interesting and perplexing as to why when we look up in the sky, we don't see a red sky, as I call it, like the red star.
Let me ask you, how do you know these stars live for trillions of years?
That's a good question. So obviously, no one's empirically observed that to be true because the universe is only 14 billion years old, 13.8 billion years old. So we think this to be true based off our understanding of stellar theory. We certainly know when stars eventually die, stars like the sun, they will eventually become a white dwarf star. Stars which are more massive will become black holes or neutron stars. And so when we look at all the dead stars that we see out there, we can kind of figure out how heavy it used to be before it died. And we know that there are no red dwarfs which have ever died yet. We don't see any stars which look like the remnants of a red dwarf star. So certainly we know for sure they live for a very long time. The reason why we think they live for a very long time is because their luminosity is so, it's like the candle that burns half as bright burns twice as long.
Candle that burns half as bright burns twice as long.
Yeah.
Okay.
Right? Because there's a certain amount of wax.
Makes sense.
There's a certain amount of fuel.
Right.
And if it's only, just a tiny little flame on
Makes
there,
sense, yeah.
it's going to take a long time to churn
That's a
through
good visual
all
to
of
be
that
thinking
fuel.
about. Yeah.
So these stars, they actually have a huge amount of mass. They're about 10% the mass of the sun. So they have a huge amount of hydrogen to burn through. But their luminosity is not 1/10 of the sun. Their luminosity is like 100th or even 1,000th that of the sun. So they're very, very dim. And because of that, they take a long time to burn through their fuel. They're also extremely efficient. Unlike the sun, they have convection all the way through into their core. So, like in your tank of water in your home that turns over and heats the water in your house, there's a convection cycle. So as you put a heater at the bottom, you'll get hot water at the bottom of the tank. It will then rise because hot stuff expands like a hot air balloon. It will expand, it will float to the top, and then it will get cooler and it will sink back down to the bottom. Now in the sun, that doesn't happen. That only happens basically at the very top of the atmosphere. When you're close to the core of the sun, it's producing so much energy. It's like a nuclear furnace that's just blasting out in your face, and nothing can sink down because the power coming out is just too intense. So we call it the radiative zone. But these stars, they're so dim that everything can churn. And because they can churn, they get to gobble up every last hydrogen atom if they want to, or very close to. All the hydrogen in the star they can use over time. So that's why we think they should last for trillions of years.
So if we rely on the sun, what do they rely on?
Well, the planet around the red dwarf, you mean?
Yes.
For their energy source, they would just have to be closer to the star to get enough energy.
They would have to be closer to the sun?
To their sun.
To their sun.
Yeah, which is this red dwarf star. So that's why this planet is actually much closer in than Mercury is around the sun. It's very, very Proxima Centauri b.
How many suns or red dwarf planets, how many of those are out there?
In the Milky Way, there's about 100 billion stars, and there's about 3/4 of those. So 0.75 of that is essentially 75 billion red dwarf stars we would estimate to be in the Milky Way.
Like a sun.
Yeah, but they're not all catalogued. We just think that like the sun, there's probably about 10 billion.
Oh, like the sun, there's 10 billion.
So let's say 10 billion suns, 75 billion red dwarfs. But to be clear, we haven't catalogued all those stars. Those are just estimates.
So right now, when we look out, what do you call it? When you're sitting outside and you're looking out what are the tools you guys use? Telescope.
Yeah.
How far out is the most advanced telescope today?
In terms of how far out can it see?
How far out can it see?
You're probably talking about JWST for that. So JWST, the James Webb Space Telescope, is this, NASA's latest toy.
That's the one?
Yeah, it's the successor to the Hubble Space Telescope, launched a few years ago. I myself am using it in October, which I'm very excited about.
You've never used it before?
Not yet.
Okay. What's special about it?
It's it's massive. It's 6.5 meters in diameter, so it's the largest space telescope we have. It's also an infrared telescope, so instead of seeing invisible light, it sees in heat, essentially. And the beautiful thing about that is it can penetrate through dust. So visible light gets blocked by dust, and in space there is a diffuse cloud of dust that kind of obscures your vision. But if you look in infrared light, you can just peer straight through it and go all the way to the side of the universe. So this thing is seeing galaxies which are in the process of forming. And so we are seeing galaxies that are of order of 100, 200 million years old, which is that's 0.1 billion years old, and the entire universe is 13.8. So this is a tiny, tiny fraction. I guess the furthest we can see back in total is actually not from this telescope at all, but would be what we'd call the cosmic microwave background, or CMB. That's a useful thing to check out. If you can Google that, you'll see this this beautiful picture of like dots, which is again like there we go. So this is taken in millimeter and radio wavelengths. And this is light, which has traveled for 13.8 billion years and is just reaching our telescopes, the light that you're seeing in this image. And so it left it's whatever was emitting it was basically a cloud of dust and material when the universe was 380,000 years old. So this is the oldest light we can see. It's actually impossible to see light before this point, because before that point, the universe wasn't transparent. It was opaque. Before this point, there were no atoms. So protons and electrons were not bound to each other. And so light just couldn't even travel through the universe before that point. So it's never possible to see light before that point.
Why is this important to astrophysicists?
Oh, this is a hugely important image. It teaches us about the origins of the universe. It's one of our strongest evidences for what we call, essentially the Big Bang Theory, the origin, understanding how much dark energy there is, dark matter there is. It's a fascinating thing about it is that it's so homogeneous. And that has been it was a puzzle for a long time. So these little differences you see in the image, if you scroll down a tiny bit there on that image, they're tiny. So this whole thing, all the light is about...
What's the red represent?
Hotter regions, and the blue is colder regions. So the
yellow is whatever intermediate.
In between.
Okay,
yeah. So this whole image is about 2.7 Kelvin. So very close to absolute zero. Very, very cold light that you're seeing here. When it was emitted, it was very hot light, but simply the expansion of the universe itself has cooled it down over time. Now, the differences here are tiny. I can't remember the exact number. We're talking like millikelvin, microkelvin differences between these regions. And those hot regions, they're slightly denser, and the bluer regions are slightly colder. And so these differences, the over-densities, are what gave birth to galaxies. If this was completely smooth, I mean, didn't see any differences here, then you wouldn't have stars, you wouldn't have galaxies. It's the fact that you get slight over-densities in different regions.
This is shown what? This is shown all of the galaxy? Or what is this showing?
That's the whole universe.
That's the whole universe.
That's the whole sky.
That's the whole sky.
Yeah.
And okay, so...
That's the whole universe in a single image.
So if that's the case, what's the end?
What do you
is
mean by
there
the
an
end?
Because
end to the
way
universe?
this shows, there's an end to a universe, no?
There's no end. This is a wraparound image. So this is like your full sky. You imagine like you do like your 360 camera.
But is there an end?
We don't think so. As far as we can tell, the universe just goes on and on and on in every direction. So it does seem, we can actually measure from this image, you can actually measure the curvature of space itself. And so an open question is, if there was a wraparound universe, you could travel in one direction in a spaceship and you'd eventually come back to the same position. So the universe could be like a big sphere, like the Earth is, like a big sphere, but in like a hyperspace kind of dimension. Now, when we look at this, we don't see any curvature. As far as we can tell, the universe is completely flat, very, very, very flat. Now, that is consistent with a universe that just goes on forever and ever in all directions. Perhaps there is an end like this table has, like it just suddenly cuts off.
We don't know.
But we don't see it.
Okay.
As far as we can tell, everything we can see, it just goes on and on and on.
So let me ask you a question. This telescope I just looked at, is it true that the cost to make it, Rob, I sent you a link, was $10 billion?
Yeah, unfortunately, it was when it was first projected to be built, it was, I think, $500 million. Ended up overrunning by a factor of 20 in cost and 16 years in launch date.
16 years it took to build it.
No. It took longer than that. It was
launch date.
It was originally supposed to launch 16 years prior to when it did launch.
Got it.
So it was massively set back, both in terms of cost and
who gets
data.
to use this? Who gets to go?
Anyone. You could use it. So you can write a proposal to NASA. There's a cycle coming up October 25th, I think the date is coming up. You just, if you want to, you just Google, if you want to, JWST Cycle 4. That's what to search for, JWST Cycle 4. And then you can write a proposal. Yeah, call for proposals. Click that, and it has instructions for what you can do to write. Anyone in the world can write a proposal.
And what are they looking for to say yes to you?
They're looking for compelling science cases to try and use the telescope to do something that only that telescope can do. Now, this is such an expensive telescope. You don't want to do something that, by the way, you could do with any other old telescope.
Yeah.
This has to be something unique that only the best telescope that we've ever built could do this one thing. That's why, you know, we're using it in October to look for exomoons, which has never been found before. We think these will be the first things. These are moons orbiting planets like Proxima Centauri b. It's never been found before. And we believe that this telescope could find moons around planets which are as small as the moons we have in our solar system, such as the Moon or Ganymede around Jupiter or Titan around Saturn. This is something uniquely that only this telescope can do. And so that's why we think we have a good case, and they agreed.
Since they have put it out there for people to use 2021, I think I saw 2021,
yeah.
$10 billion, 16 years, you know, all these things we're talking about this. What have they discovered? What has been their biggest discovery that any kind of astrophysicists have found?
There's been a huge, it's hard to know where to begin with. It depends on which field you're talking about. But I think some of the most newsworthy things people have been talking about have been the discovery of these galaxies and black holes in the very, very earliest points in the universe. So JWST is like a time machine, as we kind of already alluded to. You're looking at light which has traveled for billions of years to reach your eye. Mm-hmm. And so some of that light is 13.7 billion years old. Now that means you are seeing a galaxy at the earliest point in the universe. Now we didn't think that galaxies should be around 100 million years after the Big Bang. That seems too soon, right? Because it takes a certain amount of time to build stars, for those stars to collect together to form galaxies, and then they have to swirl around, and you have to form this disk, and then you have to have the black hole in the center, and there's a lot of structure there. It takes time to build that, but we are discovering galaxies in these images that JWST are capturing. They sort of shocked us, because we just didn't expect these things to form as fast as they did. And similarly, there's detection of black holes, which are very massive objects as well. That takes time to build a black hole, right? You can't just have one star collapse and make a giant black hole. The biggest black hole you can make that way is probably like 10 times the mass of the sun. But we are seeing black holes that are millions of times the mass of the sun. So the only way those could form is the combination of stars coming together, smashing together and forming by coalescence these giant black holes. And we're seeing those in these images as well through quasars. So those are challenging us. We're trying to figure out, like, did we screw something up in the theory? Is there some new processes we don't understand? And I think that has been, you know, that's what good science is. It's like challenging existing theory and proving that maybe there's something else out there we haven't thought of.
Got it. So, and you guys are going when, you said? What month?
October. So
October,
we're coming up pretty soon.
2 months. Are you excited about it? Is it like exhilarating or?
It's pretty wild, right? Because I'm going to look up into the sky. This thing's actually not even orbit of the Earth.
Where's it based at?
It's orbiting the sun.
No. Where is the actual telescope at?
Yeah, it's orbiting the sun. It co-orbits the sun along with the Earth. So there is a position. It's kind of, imagine the sun and then the Earth, and then behind the Earth, there's a gravitational well called...
So it's in space.
It's in space, called L2, Lagrange point 2, and it lives in this little gravitational well. It's about 4 times further away than the moon is.
So this is 4 times...
Yeah. That's why it was expensive. That's why they takes $10 billion to do this.
Who paid for it? Who funded it?
It was mostly funded by the US taxpayer. Yeah.
So we funded it?
Yeah. But ESA contributed as well, and the Canadian Space Agency contributed as well. But it was primarily NASA.
Mostly from NASA?
Yeah.
Okay. And so where do you go to be able to use it?
You don't have to go anywhere. You just tell them what you want to do. You write a program, you write a proposal, and then you work with the engineers.
They give you the findings?
They give you the data. So the way it works for us is you get to ask, how long do you want to hold on to the data privately for? The maximum is 1 year, because it's US taxpayer money, so you can't hold on to forever. So we said, okay, we'll take the full year. We're going to have the data just for ourselves for 1 year. Then after that year, it becomes global. Everyone can access that same data point after that point. But during that year, we're obviously kind of in a time crunch to try and analyze the data and get it out to everyone.
Does the telescope have any form of AI where it's individually learning and getting smarter, or no, it needs to be, it needs to be influenced to be able to seek?
Yeah.
Why didn't they create a self-learning technology as a telescope that's constantly working every second of the day.
There are some telescopes which are trying to figure out how to use smart scheduling like this. There are some telescopes which are called survey telescopes, where they basically do one thing, but they do it over and over again. And they just take an image of the sky, then they shift, and another image of the sky, and they shift. And you want to do that in a very clever way. So that's where AI is coming in. You can use AI to optimize how you tile the sky and deal with, maybe Jupiter's in the way on July 5th. So you don't want to point at that region of the sky when Jupiter's photobombing your image. So you need to account for all these different variables, and that's where smart scheduling comes in. But for JWST, it's not that type of telescope. It's not a survey telescope. Yeah, Rubin's a good example of a survey telescope. JWST is not a survey telescope. It's one where human beings write in ideas, and it's supposed to be for the most innovative and fresh perspectives that humanity has to offer.
So is it like ChatGPT for astronomers and astrophysicists, that you have to ask for it to give you the information and go get it for you? Or is it more like Google? Hey, what is this? Let me go get it. To put it in context where the average person understands it, how does it, like, even when you want the request, right? Here's what we want the findings to be. How long does it take to get it to you? Is it overnight? Is it one day? Is it a month?
They would take a few days. I mean, the whole process from start to finish, let's go through it quickly, is, there's this call for proposals. Astronomers all around the world and everyone else can write proposals to say, look, I want to do this, I want to do this, I want to do this. So we put in our proposals. I think it's 3 or 4 pages of text. And you say, here's what I want to do. JWST is the best thing to do it, and we're sure we can do it. So this is it's like a business plan, your business plan for the telescope. So you put that in, and then it goes to a committee of astronomers who rank these proposals. And I think last year, there was somewhere between 10 and 20 times more observing proposals than there was available time on the telescope. So they couldn't give everybody the time. They had to cut it down by about a factor of 10, what people asked for. So they only take the top 10% best ideas, which are ranked by human beings, no AI involved. And then those best ideas are eventually scheduled onto the telescope. And again, that's the engineers who work at Space Telescope Institute, Johns Hopkins University, down there in Baltimore. And those guys then help you schedule these observations. They collect the data. As soon as they collect it, they have to transmit the data back to Earth, has to get some preliminary analysis by Space Telescope Institute, some calibration, and then it comes to my computer. And then we've got a year to publish it.
To do whatever.
It's all humans. It's all humans.
Okay, that's interesting. That we don't. That is so weird to me that we are in this season of technology, of being able to make videos with your face and your audio and your voice, and it's so much technology that's self-learning, continuously getting smarter and smarter and smarter, that this is waiting for us to feed it to get smarter. So maybe, when did they start building this? How long ago was it when they started? You said 16 years ago?
Probably over 20 years ago.
Over 20 years ago.
Yeah.
So maybe, so much has advanced that some of the stuff that they used, I don't know the world to know how long it takes to build something like this. Is there another one right now in the works that's like the super innovative one that they're building? Yeah,
there's a successor to this one that's being planned called the Habitable Worlds Observatory, HWO. It's not being built yet, but people are starting to plan out what it might look like and come up with designs and things. And this guy will try and take an actual photo of an exoplanet from afar. So instead of flying a spaceship past to take a photo, it's going to try and block out the starlight. So imagine, like, if you look up at the sun, you put your thumb over the sun, you could actually use that blocking out of the light to make it easier to see stars or whatever nearby. It's going to try and basically do the same thing for stars. So try and block out the star, but not block out the planets, which is very, very difficult to do both of those things. A planet is 1 billion times fainter than a star.
A planet is 1 billion times fainter than a star.
Yeah. So that the Earth is. So that's a huge compression factor that you have to remove starlight.
Got it.
It's very, very difficult.
And the launch date for this is 2040. By the way, so when we're talking about 16 years from now, when we're talking about the Proxima Centauri B, right? Is there any technology right now for us, even with the one you were talking about, the telescope, or the new one that they're coming out with, where you're going to be able to look at it and say, what is there? That's a lake. That's an ocean. That's a mountain. Is there anything like that that'll be here by 2040?
Not unless we do something radical. So there are some interesting ideas. So one crazy idea, which maybe you'll like, is the idea of turning the sun into a telescope. And I've certainly proposed a similar idea of turning the Earth into a telescope. I'll tell you the sun one first. So the sun is a gravitational mass, and so all gravitational masses bend light. So actually, if you go all the way back to, I think, 1929, Arthur Eddington, who won the Nobel Prize, I believe, for this, showed that for the first time. During a total eclipse, he took a photo of a star that was close by to the sun, and then he took the same photo of the star at a different time, and you notice it shifted position because the sun, when things are close to the sun's gravity bends light into a curve around them. So gravity bends stuff. Now, anything that bends light is a lens. So just the same way, if you're wearing glasses or a magnifying glass, it's just bending light. Sure. So the sun can be a lens. You just have to find the focus point. Now, the focus point ends up being way beyond the orbit of Pluto. So it's in the very outskirts of the solar system. But in principle, if we flew out there 500, 600 times further away from the sun than the Earth orbits the sun, so really far out there is a point which is a focus point. And that's a gravitational lens where we could put a telescope and it would effectively collect the entire power of the sun in terms of the amount of light it could receive. Now, that thing could resolve kilometer scale, rivers, lakes, mountains, that kind of stuff on the surface.
That's what we need. I mean, we need to see what's out there, right?
Yeah. So this is an interesting proposal. It's very difficult to fly that far away from the Earth and have infrastructure. It's just kind of a little bit sci-fi at this point to have significant space infrastructure that far out from the sun. The furthest thing we have is like Voyager 2, which is now basically dilapidated. It's falling apart. We can barely hold on to simple transmission with it. It has these magnetic tapes which are falling apart on it. Its batteries are running out. So, it's very difficult to have stuff out there, but that would be the ultimate telescope. And so I think if there are aliens out there, that would be the telescope they would build, because you can't build a better telescope than an entire star.
Can that happen during our lifetime?
It would take an enormous investment.
What's enormous?
I think you'd be looking at, Apollo era levels of funding for this single objective. So you're probably talking about, maybe $200 billion, something like that.
So what? I mean, what $200 billion is what is worth to us? Apollo was what? $25.8 billion in 1960. Right? Between 1960 and 73, approximately 257 billion when adjusted to inflation. I got you. Okay. Yeah. So $250 billion to do this. The question then becomes, if you put all the countries together, the top ones, top 20 powerful, US, China, Russia, you take France, Germany, all the guys that have money, India, and you say, hey guys, collectively, let's do this. Yeah. What is it worth for us to know if there's civilization out there?
Yeah, it's hard to answer the question, what is the value of blue sky research sometimes? I know people ask that a lot. What is the value of NASA? But look, here's the thing. Every dollar that we've put into NASA, on average, returns to the economy, estimates vary, but between $7 and $14 per dollar.
How do they measure that?
By looking at the patents, the material development. I think you look at medicine, materials, communications, environmental monitoring, and even tech consumer products.
You know what that does to me, Rob? Here's what it makes me think about.
In these uncertain times, if there's anything we need people to believe the future looks bright. So if you've heard about me saying this mission to you, we're on a mission to get 1 million people to wear this gear, and this is what we're doing. If you buy one of these hats, there's a category of buying one hat, getting the second one free. If you haven't yet worn this gear publicly, go ahead and test it out. Buy some of the gear, wear it in public, and see how many people will stop by and say, you also watch Valuetainment? You also follow PBD Podcast? I do too. Place your order. Go to vtmerch.com, click on the link above or below, place your order, and represent the VT and the PBD Podcast gear.
Do you know who AOC is in America?
Yeah.
Okay. AOC wants us to put $30 trillion with Bernie Sanders. Type in climate change, $30 trillion. Okay. Now, if you put climate change, $30 trillion, right? That is their plan. Zoom in a little bit so I can read it. Overall global damage are estimated to be $38 trillion with a likely range of 19 to 59 trillion dollars, right? But I'm talking about the Green Deal. Green Deal. Yeah, just put that in there. Let's see what comes up. So the plan was, it was going to cost us, the U.S., $30 trillion. Can you find that, Rob? Somewhere just type in AOC climate change, $30 trillion. So this whole thing that was proposed with $30 trillion, just control F30 to see if you find it or not. Okay, maybe I'm going to find it, Rob. But this whole thing with $30 trillion that was proposed to us for climate change, okay, there is no promises like what it's going to do. There wasn't like, here's what we need to do. Here's what we're going to get. this is what it's going to come with it, right? There was nothing like that. It was a lot of, wishy-washy promises of what it is. But if you sat there, and I'm telling you, you told the taxpayers, hey guys, let me tell you what we're going to do. Would you like to know once and for all if there is civilization out there? You want to know if there's aliens? Guess what? No more Area 51. No more anything like that. What if we could tell you on every single planet out there, if there's water, ocean, people living, aliens, any of that stuff, what if we could do something? What would be that worth to you? Then the taxpayer would be able to sit there and say, I think a lot. Okay, cool. If it's worth a lot to you, is it worth $250 billion over the next 20 years? I think so. So here's what it's going to cost. We have to collectively pay for this. U.S. has committed to the $250 billion is going to, $70 billion of it's going to be U.S. China's committed to this much, and this is committed to this much, and here's what we're going to do with the next 20 years. I think a lot of people would be for it.
Yeah, you're singing my praises. I would love that to be true, for sure. I think I do have some, A is, can we collaborate with these other nations, right? Because collaboration internationally, especially on these science projects, has been at an all-time low. It's really struggling right now because of all the political challenges that the world is facing. So that's one issue. Another issue is, I'm not sure that the US public are as enthusiastic about planets as maybe you might imagine. There was a Pew poll in 2023, for instance, that showed that about 69% of Americans do believe that NASA and America should be a leader in space. But there was a number in there in this 2023 Pew poll, maybe you can try and dig it up, that found that it was something like 17% thought that looking for life in the universe or looking at planets was an important priority. So there were people out there who do think it's cool science and worth doing, but I don't think it's most people's top priority. I think they normally think about tourism, space tourism, maybe, having human astronauts go to Mars, things like this, and maybe higher priorities. Obviously, I feel like looking at planets and life in the universe is incredibly important, but...
so what did people say? What was the percentage of people that are interested in that?
I think it was around 16, 17%, something like this, that thought that looking for life around planets was a top priority. 16
or 17%?
Around this kind of number, yeah. But that was from memory. I looked this a while back. There you go, yeah.
Search for life and planets that could support 16%. What's the light blue, the lightest blue, and the middle one? What is it? So top priority, important, but lower priority, and not too important. Okay, so let's just say 16 plus 44. 60% is somewhat important, right?
But what do you think it was during the Apollo era? Because that's the comparison. During the Apollo era, what fraction of Americans thought that getting to the moon was more important?
Who was president at the time?
Right, so there you
who was the president?
During the moon landings?
Apollo era, who was the president at the time? John F. Kennedy.
Yeah, well, he not during the
I know he did, but he sold it, right? So meaning someone has to cast a vision. So say I'm a president, and I get up and I say, listen, so many of you want to know about aliens, right? I would literally talk to the American people. I say, you want to know about aliens? How much you want to know about aliens? All of you guys are interested in Area 51. What do you want me to do? You want me to go into Area 51, grab a camera here, and just kind of do it live and show you everything? Of course we can't do that, but how about this? What if instead of us sitting here claiming, give us $95 trillion to fix climate change, which is not even a guarantee, and you're going to have to pay all this money for the next 20, 30 years? What if I can tell you hard cost, $250 billion, next 20 years, we're able to build a telescope to put it, next to whatever planet it is for us to be able to look at every single planet out there to find out where is there actual civilization or aliens living there? What is that worth to you? I would like, as a president, for us to be able to figure that out and get the answers to you within 2 decades, because that could protect our civilization. I think today, if the right president sold that, I don't know why. Maybe I don't know what's in. Maybe they put shrooms in this tea. Maybe there's ayahuasca. Rob, what'd you put in this tea, Rob? Did you put something in there? Maybe it's what I'm eating right now.
But I love the enthusiasm. I'm not going to argue with you.
I would love to know,
it'd be great.
But who would say no to that, though? I really think so many people. Okay, so let me go back to another thing you said earlier. So you said the Earth has roughly 1 billion years left. Okay.
Yeah, for complex life.
For complex, what is complex life? Like
multicellular, not just bacteria. I think beyond that, you can imagine some bacteria clinging on in caves and deep underground. But yeah, creatures, animals like us, I think there's less than 1 billion years.
In about 1 billion years, no matter what we do, everybody's wiped out.
Yeah, it's actually CO2 exhaustion that wipes us out, strangely enough.
CO2 exhaustion.
It's because we lose CO2.
Because of us using it ourselves.
No. It's what happens is as the sun increases in luminosity, this has actually been going on its entire history. So when the Earth, people often say, well, the Earth had much higher levels of CO2 in its past. It's true. But the sun was cooler in its past. It wasn't as luminous. And they're anti-correlated to each other. So as the sun increases in luminosity, you have this CO2-rich ball of atmosphere around the Earth. As it gets more and more luminous, it causes more evaporation of the oceans, and then you get this rainfall come down. As the rain comes down, it dissolves carbon dioxide out of the atmosphere, and you form carbonic acid.
Sure.
That then hits the ground and forms limestones. So carbon gets pulled out of the atmosphere from precipitation and other weathering processes, and it basically gets locked up underground. And that is forced by the sun's increased luminosity. So as you increase the luminosity of the sun, you decrease the carbon dioxide in the atmosphere. We've seen that throughout history, and it will continue to happen. What eventually will happen, that CO2 levels will drop below about 10 ppm. So currently it's about 400 ppm in the atmosphere. Eventually it will fall below 10 ppm. Once that happens, plant photosynthesis ends.
At what point do we die? At 10?
About 10, just because you can't have photosynthesis anymore.
And we're at 400 right now.
Yeah.
So between 400 and 10, we're okay?
Yeah. Well, plants are okay. It's not really so much us, it's just you can't have plants. If you can't have plants, you can't have us.
Okay, and then the sun. When you look at the articles, you'll read articles saying the fact that the sun's got 5 billion years left, right? I mean, it says, when will the sun die? And you'll kind of pull it up, and there's a bunch of different articles written about it. Here's what will happen when our sun dies. Billion years from now, right? It says 5 billion years.
Yeah.
The sun gives energy to life on Earth, and without the star, we wouldn't be here. But even stars have limited lifetimes, and someday our sun will die. You don't need to worry about the solar death anytime soon. It's likely not to happen for the next 5 billion years, et cetera, okay? So Earth, 1 billion. Sun, 5 billion, according to what we read. Maybe you can correct me, and it's a different number. Climate change is a big topic. Okay, a lot of people are talking about climate change. You give me $93 trillion, I can fix the problem for you. I mean, a lot of politicians in America, I don't know if you're in your country, you have politicians in our country.
Well, I'm American. I'm an American now.
I mean, UK, where you came from.
I originally am British, but now I'm naturalized.
Where are you based out of?
New York.
Okay, so here you see it with all the politicians that want all the money to be able to fix climate change. As an astrophysicist, you're not a politician. You're not a political guy. You're a scientist.
Right,
you're an astrophysicist. When you hear politicians make promises that they can fix climate change with $93 trillion, I'm curious, how do you process that?
Yeah, I mean, this is a political question, so I'm not an expert in politics. What I believe is true is that the atmosphere is being affected by human activity on this planet, and we are fundamentally altering the chemical composition of our planetary atmosphere. That is a very dangerous experiment that we are doing, and we are not sure what the consequences of that will be, but many of our models, our best models of the projections, generally look very bad for the future in terms of the economic impact and hardship it will have on the US, but all over the world. I mean, you're seeing it already. Like I know in Florida, like where we are right now, a lot of insurers are running out of the state, right?
No
running
question.
out of Miami.
Here in California.
Yeah.
California for fire, here for hurricane, additional things.
Yeah, for flooding, things like this. And so that's, I think, one of the things I worry about is I don't know with this plan you're talking about whether investing that amount of money will fix this problem. It's not obvious to me how we can fix this. The only way to really fix this is to get the CO2 out of the atmosphere that we've put in. That's the only true fix. And we don't have a technology which can do that in any feasible economic sense.
Let me ask, who is the most qualified scientist to be able to actually tell us a way to be able to address it? Is it what kind of scientist would it be?
I mean, we have an office just around the street from us called NASA Goddard Institute for Space Science, NASA GISS. And one of the directors there, Gavin Schmidt, is a good friend of mine. Our kids go to the same school. He's the director of that institute. And they do all the analysis of the measurements of Earth's climate and the temperature. And they make projections about how the temperature and the sea level and hurricanes and things like this will change over time. So this is where you can, if you go to this website, NASA GISS, you can actually grab all the data from any measurement measuring stations they have, you can grab the data and look at it yourself, look at the trends, look at the global trends, sea level, whatever you want to look at. And their models, obviously a lot of the models that they're using are informing, I assume, some of the policy that you're talking about. And so I think, I've had Gavin come onto my podcast and talk about some of the work he's been doing, but he's not really thinking about solutions. This office is not an office which is planning, like, here's a mitigation strategy. They're just collecting the data and telling you what's likely to happen and what's currently happening. But in terms of mitigation, I think that's where you're seeing both politics and even some corporations start to come in and add their own inventiveness of how to solve this. So you've got things like direct air capture. These are these giant wind turbines that are trying to, like, suck air out of the atmosphere and pull the CO2 out. And people are trying to innovate and think of how to do this. But none of these technologies, at least for my money, are anywhere near the level needed to reverse, if you want to go back to pre-industrial CO2 levels, you're talking about using basically 100% of the Earth's entire electricity supply for the next until the year 2050 continuously, even assuming you had 100% thermodynamic efficiency machine. So it's just ludicrous. But it's so far. I did a whole video about this. It's so thermodynamically, we can't reverse the damage we've done at the atmosphere.
We can't.
Right now, with our current technology, it's fanciful that we could ever get back to pre-industrial levels with the limitations of our current energy supply.
So let me qualify what you just said and correct me if I'm off.
Yeah.
One, you're saying civilization has negatively impacted climate change. One, you're saying that. But two, you're saying all the money in the world couldn't fix the problem today to eliminate the CO2. All the problem in the world, all the money in the world wouldn't be able to fix that today.
I think if your version of fix is reverse the damage truly and pull the CO2 out, then I don't think we can fix it.
Well, you're saying that is the only way to fix it. That's what you're saying, though, right?
I think our best bet at this point is try to mitigate.
Preventative?
Like, you can't. There's going to be pain. But how painful do you want it to be? It's going to be pain whatever at this point. I think there's just no way around that. It's going to be painful.
That. What do you mean by that?
You can, there's these different scenarios. So you talk about like RCP scenarios are like these climate projections, and there's like RCP 3.5, 4.5, and the worst case is 8.0 that I've seen. And these are projections as to, like, I think 8.0 is like the business as usual. Like, you basically just don't give a damn about the environment and you just keep like doing whatever the hell. 8.5, you just do whatever the hell you want to the atmosphere and burn as much coal and oil as you possibly want. So I don't think that's very realistic that we're going to be on that scenario. But even already the 4.5 and the 2.6, which have pretty serious consequences for the planet. Yeah, even those, I think we're struggling. I think we're not on brand for. I think we're already diverging away from those scenarios in terms of our impact. And these are going to have, I'm not sure what the numbers are, but you're talking obviously trillions of dollars, as you said, of potentially damage to homes, to businesses, to the economy. That's what I worry about. I don't worry about this as an existential risk. I think people sometimes think like humanity is going to be extinguished by climate change. I don't think that's likely to happen. I just think we're going to make our lives a hell of a lot harder, and the economy is going to really struggle under the burden of so much damage happening to our buildings and
in our lifetime.
Yes, I think so. And certainly in my lifetime. Yeah, I expect that to happen. Yeah.
Okay,
it's already happening. I think you're seeing.
You're saying if we go the way we're going right now, you're saying we're still going to be around for 1 billion years. That's what you're saying.
The Earth will be.
The Earth will be. Will we be around?
And life will be. I don't think humans will be around.
Why not?
Years. Well, the species of humanity depends how you date it, but less than 1 million years old, I would say. So no species has ever survived in the paleontological record for 1 billion years. There's no single species which has persisted that long.
Purely for self-destructive purposes, or it could be an outside?
Species just change, evolve. You don't have things evolve over millions of years timescale. So even if there was a descendant of us, there'd probably be many, many descendants of humanity by that point, right? We'd probably split. You can imagine some grave disaster happening to humanity in the future. Maybe it's climate change, maybe it's something else, but maybe some complete reset, and we diverge, we go back to living on continents separately from each other, and then they would eventually speciate and form separate species over millions of years from each other. I mean, there's very long timescales, and then those descendants would evolve and adapt into new species, and they'd be competing with other descendants of other species. If things evolve and adapt and change over time to the changing environment.
How different is that than what we have today?
How is it different? I mean, it's not different. Things are evolving right now. Yeah, I think everything's constantly in a process of
You're
flux.
not saying we'll be extinct. You're not saying that. Or you're saying that is also
it's
a possibility.
I don't have a crystal ball. I don't know what's going to happen.
The possibility of extinction would require what? An outside event? You're thinking comet, you're thinking, are you thinking more outside, or are you thinking we will self-destruct and we will destroy ourselves?
Right, so I'm a little bit maybe, this is more speculation. Let's just put that out there.
Sure,
because we're speculating about the future.
No question about it.
But yeah, my personal view on this is that intelligence, which we are, an example of an intelligent being on this planet, has not been on this planet for a very long, for entire its history, basically, until fairly the last few 100 million years. You start to see things like octopus, ravens, smart birds, dolphins, humpback whales, and humanity. All of us are intelligent species. Now, it seems like if you go back 600 million years ago, everything was basically single-celled on this planet at that point. So you have these major transitions that happen in Earth's history. Now, my kind of crazy tinfoil hat theory, and I'm not an evolutionary biologist by any means, but my crazy tinfoil hat theory, more from an astrobiology perspective, is that intelligence bestows survival advantages, clearly, because we've dominated this entire planet through our intelligence, not through physical strength by any means. And therefore, anything that bestows an evolutionary advantage will persist. Maybe it won't be humanity, but other species will continue in some form to have intelligence. And so that's really interesting. It means that even if it won't be us, I think there will be intelligent creatures on this planet that will go through probably periods of rising and falling of civilization over the next billion years. Now, that's pretty interesting because it means, there'll be people one day going back to the moon. Maybe it's like an octopus or a squid or a bird or a raven, some descendant of those, landing on the moon and seeing the Apollo landers and thinking, this is pretty wild. There must have been some kind of ape that, look at these footprints, some kind of ape that was walking around on the surface of this thing. We are not the first ones here. And maybe they'll actually, struggle to get to the moon because we've burnt most of the oil in the ground. And they're thinking, hey, where's all the uranium gone? Where's all the oil gone? Why is it so hard for us to get an industrial age going? It's almost as if someone was here before us. And so, yeah, I do think intelligence will persist. And that gives me a lot of hope when I look for alien life out there, because if you're a pessimist and you think nuclear war's around the corner, or we're going to extinguish ourselves through climate change, whatever it is, then maybe you'd put humanity's lifespan at maybe 1 million years or a few thousand years for technology, something like this, which is a blink of an eye in cosmic timescales. It's nothing. And therefore, when we look out for aliens, if they're the same as us and they extinguish themselves so quickly, it's hopeless. We're never going to find anyone. But if intelligence just keeps popping up, it goes down a valley, then it comes back up, and it rises and falls, just as evolution has shown us in the past, then that gives me some hope that we might detect something out there if intelligence really is a persistent phenomena. And so I kind of like to think of intelligence as an infestation. Humanity, I think, could be an infestation in a sense, not in a sense that I'm comparing us to a rodent and we're some poisonous thing to this planet, but that we're very difficult to eradicate. We're in every continent, we're in every environment you can imagine on this planet. We are there, we have buildings, we have structures, we are farming, and we adapt to those environments and we thrive in them. And I think to totally remove humanity from this planet, I don't think it's possible. I think we're going to persist. But it will be descendants of us, and they'll adapt and evolve to new conditions, because that's what biological evolution tells us will happen.
It'll be descendants of us?
Yeah.
Yeah. But that's not anything out of the ordinary.
No, of course not.
We are descendants of somebody.
Yes.
We are descendants of somebody.
And we are different from our ancestors. Biologically.
Sure.
Yeah.
Biologically? Tell me what you mean when you say biologically.
Well, just the size of our head is significantly larger than it was 1 million years ago.
Why do you think it was? What's your reasoning for it?
I mean, we know that to be true, obviously, from collecting skulls. Yeah.
Why?
Why? Because it most likely provided an evolutionary advantage through natural selection.
Got it.
So having a larger brain gave you an advantage that meant you could outcompete the next tribe over, right? Because you could build better traps and you could capture more food.
There was a guy in the Army who wore an 8.5 hat. He did not have an advantage. I'm not going to lie to you. I remember this guy. And we had a nickname for him, and I won't say it, but at that time, we'd always give him a hard time. But man, we were 7.25, 7.5. This guy was 8.5. He was legit, but wasn't good at math, wasn't good at a lot of things. So Elon Musk, okay, he wants to, he's a humanist, right?
Yeah.
Colonizing on Mars. He's a very smart guy, okay? This is not a guy that's just, have 3 shots of tequila and says, hey, guys, I'm going to go colonize, and I'm going to have life on Mars, right? Mm-hmm. For somebody as smart as him to say something like that, what are his hurdles of that becoming a reality?
Mars is a very hostile environment to live on. I mean, it's much harder to live on Mars than it is Antarctica, put it like that, right? Antarctica has an atmosphere that we can breathe. That's the most obvious basic thing. Its temperature is actually similar to Mars. It's not that different from Mars, the temperature in Antarctica to Mars. So the temperature is very similar, but Antarctica is covered in ice, so you've got plenty of water. So you have access to water, you have breathable air. All you really have to do is wear a coat and some protective gear, and you can survive in that environment. You're not going to survive in Mars under those same conditions. Mars is a place that has no surface liquid water, as far as we can tell. There's ice on the polar caps, but how much we don't truly know. It doesn't have, even the atmospheric pressure is so low that it would kill you, let alone the lack of a breathable atmosphere. And on top of that, it lacks any, there's no boat that can come and save you. Like if you need, infrastructure to be delivered or water or supplies to be delivered quickly, it's just totally inaccessible. It's going to take 18 months or something to get the next care package delivered. So it's going to require, it's going to be the greatest survival challenge for humanity.
When you hear him say that, what do you think?
I think it's it's some of my colleagues kind of think it's ridiculous and think it's just totally crazy that we'll ever do this. I've always felt like it was, if someone wanted to spend their own money to try and do it, like all power to them, let them try and do it. I get the philosophy. The philosophy is, as long as we're all on planet Earth, we're at risk. Because all it takes is one giant meteor or one nuclear war or whatever cataclysm you want, and we're all gone. And so if your objective is to preserve the species, then it totally makes sense that you would want to have a second base. And whether that base be on the moon or Mars, I don't really have a strong opinion, but I think there are definitely advantages on Mars because it's a higher surface gravity. It does appear to have a bit more water. The temperatures, there is some atmosphere at least, whereas the moon has no atmosphere at all. So I think but it's further away. So that's another challenge to how do you actually get there in the first place? How do you actually service it and have infrastructure go back and forth? But I think it's a cool goal. I don't want to live on Mars. I mean, like I said, would you want to live in Antarctica? Like if someone said, do you want to live in Florida? Do you want to live in Antarctica? I don't want to live in Antarctica. And I certainly don't want to live in a place that's even worse than Antarctica, which is Mars. So I have no desire personally to live on Mars. It'd be cool to visit for a week, but it's so far away you can't really do that. So I don't know, all power, if someone wants to try that, go for it. And, people are lining up coast to coast to be the first astronauts to Mars. I think if you put out a call for astronauts for Mars, there'd be no shortage of volunteers who'd be willing to end their life on Mars if that's what it took to go there. And you need people like that to push the envelope. I just don't want to do it myself. And that's where it's like you have to divorce maybe how you feel about something versus someone else putting their life at risk.
Do you have any desire to go into space or no?
I'd love to go to space, yeah. I'd love to do a cruise in orbit, see the Earth from space. It's been a dream of mine since a kid, but only as a paying probably tourist, I expect that to happen. And I would be okay with that if it became, something where you could spend, I don't know, $10,000, $20,000, go up, do a few orbits.
Nothing to be out there for a year and explore and, as a big project, that's not something
No, I mean, you've seen these Starliner astronauts there, which are stuck there at the moment.
Yeah, the Boeing one. I saw that, the lady and the guy.
Yeah, so
probably
Suni Williams.
25 January, they'll be able to come back.
And they're probably stuck there till February, it looks like at this point, which is...
Stranded in space. NASA doesn't see the Starliner astronauts that way. NASA doesn't say
they don't like that word.
Yeah,
but I think they are kind of stuck there for the moment, unfortunately.
Yeah, but they seem pretty chill about it. They don't seem like
they're trained for that. They're trained.
So
for
let me ask you this question. So do you think man landed on the moon?
Yeah, 100%.
You're saying 100%.
Uh-huh.
Tell me why you say 100%.
Because we can see from you look at imaging of the surface of the moon. So you have like these orbiters which are currently going around the moon. Again, you can download the data. Anyone can download the data, this NASA public data policy that we have. And you can download that data and you can see the tracks of the rovers, of the astronauts as they drove around. And you can line them up to the video footage of them driving around the surface. You can see the landers. You can see, the infrastructure that was left there. There's even mirrors that were put on the surface of the moon. It's called the laser ranging experiment. And they left these mirrors there, and we actually bounced lasers off the surface of the moon, off these mirrors. And using that, we can measure how far away the moon is. Every day we could do that. So we can measure how far away is the moon today. And we've been doing that for the last few decades. And as a result, we know that the moon is receding away from us at about 1 inch per year, about 4 centimeters per year. And this is due to the tides that the moon raises on the Earth and dissipates energy through the tidal action on the planet. So this is actually, one of the most amazing experiments, I think. It's actually now getting quite dusty. They can also tell from the lasers the response time is not only getting longer, but the amount of light returning is diminishing. So they can tell that dust is slowly accumulating on these mirrors, and even infer from that the micrometeorite rate that's happening on the moon. So when you look at all the amazing stuff we can do, there's obviously moon rocks that we have. We know about the origin of the moon from the moon rocks. We took those moon rocks that the Apollo astronauts brought back. We measured the isotopic ratio of oxygen 18 to oxygen 16 from those rocks. And by looking at that oxygen isotope ratio, we were able to tell that it was identical to that of the Earth. And that was obviously there's many of the differences in the rocks, but that particular ratio was identical. And that told us that the moon used to be a part of the Earth, which is pretty wild. So actually the origin of the moon was that it was at one point in its history part of the Earth.
What happened?
Right? So this is called the giant impact hypothesis. So it's thought that when the Earth first formed, it was actually larger than it is today. Would have been maybe we call it a super Earth. And it was this big ball of molten lava. And there was this episode in the history of the solar system called the Late Heavy Bombardment that we believe happened. We can see that because we see Mercury has been covered in meteors. We can see lots of evidence from simulations of looking at how Jupiter moves through the solar system. So we have lots of evidence that there was this late heavy bombardment. And basically, there was just a lot of crap around, just a lot of stuff moving around the solar system. And this Mars-sized planet that we call Theia, a Mars-sized planet, drifted too close to the Earth, or the super Earth, smashed into it. And that Mars-sized planet basically totally vaporized. It was destroyed in totality, but it knocked off a huge chunk of the Earth. And that huge chunk is what formed the moon. And that's why the moon has the same isotopic ratio in its rocks that the Earth has.
That is this I'm looking at it right now, giant impact hypothesis. Rob, just pull up the
theory, yeah.
The Wikipedia to it and show the picture. Is that kind of what you're saying to the right?
Yeah, I think most of the time you see a simulation, it's actually more of a grazing impact than a head-on like that. Just because people experiment with the geometry and see how the outcomes are in these supercomputer simulations. But yeah, that's essentially what you're looking at. This kind of incredible collision, which have happened 4.5 billion years ago.
Wow, I'm looking at these simulations right now. There's a bunch of them online.
It's possible that actually life had already been on the Earth at this point, and it was basically totally wiped out from that impact.
What?
And then life had to get going again after the impact. So that's a really interesting question. Did life form before the impact and get totally wiped out?
What do you think?
I have no idea. I mean, it'd be a huge discovery if it was true. And we have no way of actually essentially observing that. But if it was true, it means that life started twice. If life started twice, it means life is everywhere. But yeah, look at this thing. It's smashed together, and then you can see this debris start to coalesce. Sometimes in these simulations, they actually form multiple moons or 2 moons. And what often happens in these simulations is, you can see we're just getting 1 moon here in this case. The moon here would have been much, much closer to the Earth. You see this?
Yeah.
It's super close. And that's why, I told you the moon is moving away at 1 inch per year, right? So if you rewind that clock back,
4
that 1 inch per year,
yeah,
and you account for the acceleration due to tidal effects, it actually ends up being right there where we see it in the simulations at the right point. This is called the Roche limit. It's basically the closest distance gravitationally where you can form an object. So the moon formed at this close-in distance where it can coalesce, and it's been gradually receding away from the Earth ever since.
David, what's the likelihood of something like this happening again?
This is one of the reasons why we want to look for exomoons. This impact could be the reason why we're all here, right? So had this collision not happened, the Earth has plate tectonics, right? And those plates rub against each other. It turns out that's probably quite critical for the emergence of life on this planet. You have this interaction of these carbon cycles and nitrogen cycles where material can be recycled as it subdues and it kind of lands on the bottom of the seabed. It eventually subducts under different plates. This is the Earth's recycling mechanism. If we didn't have this, when something died, like a whale, and it just landed on the bottom of the ocean bed, its carbon could potentially be stuck there forever and just locked up forever. And eventually there'd just be no carbon left for things to make plants and trees and animals out of. But the fact is that reserve of carbon gets subducted back into the magma and then gets re-released through volcanism. So this is one of the ways in which the Earth recycles material. Now, had this impact not happened, it is possible that we would not have plate tectonics. The reason being that rather than having a series of very thin lids like this, which can rub against each other, it would instead just form one very, very thick, giant lid all the way around, which couldn't move. And we think that's what's happened to Venus. If you look at Venus, it just has one giant, thick lid. We call it a stagnant lid. It has no plate tectonics. That's why probably it's not a very hospitable place for other reasons as well. And so if Earth had formed a stagnant lid in the same way Venus did, which probably would have happened without that giant impact, I think, then none of us would probably be here in terms of complex life on this planet. So it seems like there's a lot to thank for that giant impact.
A lot to thank for that giant impact. But it's also very likely that there could have been civilization right behind it. Would anybody have survived that impact?
I don't think there would have been a civilization then, because Earth formed, let's say, like 4.6 billion years ago. This happened at 4.5. So you've got 100 million years at most for life to get going. And it took
It's plenty.
Is it? I mean, it took 4 billion years to get from single-celled organism to us the second time around. Maybe there was a first time around, but the second time around, we know for sure it took 4 billion years. So can it do it in 100 million years? That seems very tight, right? You're asking for a factor of 40 quicker for evolution to play out.
It's amazing. Like when you actually think about it, your life is like a split second.
Right.
It's like in the bigger scope of things, we are just regular.
I know.
Like this. Listen, You think you're important. Relax, buddy. You're out of here. Next.
Right.
It's so wild when you look at it.
In time and space.
Yeah, it's so interesting when you look at it from. It's actually humbling, for you to have some perspective when you really start thinking very highly of yourself. And say, I got this degree, I made this much money, I'm this, I'm doing that. Yeah, you're not that big of a deal, bro. Just relax.
Well, have you ever heard of Carl Sagan's Pale Blue Dot speech? You never seen this? Maybe check it out afterwards. You should listen to it, guys, online. It's a wonderful speech that Carl Sagan gives, and it's a photo of the Earth taken from about the distance of Neptune and the outer edge of the solar system. And this is a photo of the Earth, and the Earth, in this image, is in that sunbeam. There it is, that little tiny speck of light. That's the Earth. And he says, he's beautifully eloquent, and he says, every person who's ever lived, every general, every religious leader, every lover, every child, every grandparent, everyone you've ever known, everyone you've ever hated, everyone you've ever loved, everyone lived on that tiny speck of light suspended in a sunbeam. And that's what we're all fighting over, right? In these wars, we're fighting over a fraction of a dot. That's what we're fighting over. And just the madness of it, when you look at it from a cosmic perspective, is baffling. And that's why I love astronomy. It is said to be the ultimate humbling experience.
How about, I know, again, you're not a geologist, but how about, again, the worries about some of these volcanoes? Like when you think about, the volcano in, what's the name of it? In Yellowstone, right? What's the name of the volcano? There's a name for the volcano.
The caldera.
The caldera, right. How about the caldera where, it has erupted 3 times. I think one of them was 2.1 million years ago, 1.3 million years ago, and 640,000 years ago. And we're overdue for it to erupt again. And every time it erupts, some 80% of America gets destroyed every time it's erupted, right?
It's a bad day.
Huh? It's a rough day when that happens. What is, what is the influence with what we're experiencing right now? We're man-made. Like we can screw it up for it to erupt once again. Do you think about
I don't think
that
there's
at all?
anything we're doing that's affecting that. That's just going to do its own thing and go off.
Whether you like it or not.
Yeah, I don't think we have any control over that. It's frustrating, but there's no way we can influence that right now. But the thing is with these, like, we're overdue. It's the same with meteors. People say, okay, we're overdue for like a dinosaur killing asteroid at this point. But the thing is, we're overdue. If you go to the casino, right, you probably gambled and gone to Vegas sometimes and played a few hands, and the gambler's fallacy, right? So if you win, if you lose a few hands in a row, or win a few hands in a row, you might think, well, therefore I'm due for the opposite behavior to happen at this point.
Yes.
Yeah. And that's a fallacy. Like, statistically, if I roll a dice and I get a 6, it has no bearing as to whether I roll a 6 next time or not. It's completely disconnected. Now, over enough time, these events will accumulate, but I certainly don't think that the fact that it hasn't happened for a long time should make you any more scared. If it had just happened yesterday, you should be just as scared of it happening tomorrow as if it had not happened for 10,000 years or 100,000 years. So the risk is the same in every single point of these kind of totally random events like this.
So you're suggesting everybody stop listening to the podcast and go to the casino right now. That's what you're saying.
Yeah.
And if they lose, keep playing. Don't worry about it. It's gonna. Good things are around the corner.
It's not exactly what I said, but you sure.
That's kind of how I took it, folks. Listen, get off the podcast, go to the local casino. So this a part of, like, look, if it's going to happen, it's going to happen. There's nothing we can do about it. But again, we as civilization, we as people, we there's a part of us that likes the next, oh my God, what if? You know what I'm saying? What's going to happen? It's like you should never go into that building. All right, guys, let's go into that building. You know what I'm saying? Let's see what's inside it.
Right.
That cave right there, if you go into that cave, rumor has it, 19 bears have lived there. And over 728 people have been killed in that cave the last 20 years. Do not go there. However, a lot of people do go there because there's around $700 million of gold all the way at the end. But I'm telling you, don't do it. David, we got to go.
We got to do it.
It's something about this.
Well, the haunted houses, you see these like people who go around these crazy like insane asylums in the middle of night, and you're thinking like, why are you doing this to yourself?
Right? Yeah, it's the commercials. You're like, do not go into the garage. The kid goes into the garage. But no, I think, have you seen a simulation on the caldera? Have you seen a simulation on the eruption?
I don't think I have.
Rob,
no.
do you have a simulation worth watching on what it would look like? I mean, see if you can find a short one, not one of the bigger ones, because the bigger ones I have.
But it's a pretty terrifying prospect, I imagine.
Have you ever walked on a volcano?
I've been to Yellowstone.
Okay.
Yeah.
So
and we've climbed a couple of volcanoes before. Yeah.
I walked an active volcano in Hawaii 10 years ago. My wife told me not to do it. I went there with a guy named Jose, with a guy named John, and a couple other people. Lexi, and I want to say Amy was with us. Yeah, and we went there. It was like the lava was right in front of us. It was terrifying. Right in front of us, and you're looking at it, and the lady in the morning says, you got to get there at 3, 4 o'clock in the morning, or else the ranger's not going to let you through. So we got there very early. And then we made it past the ranger, and he says, don't do it. And he says, if you smell something that smells like this and it starts raining, turn around. It's not good for you to be there. And then he says, on the volcano you're walking, if you step on it and if it capsules, like if it breaks, you're dead because it just sucks you in. One of our guys, Jose, we're walking. At this point, we've been walking for 5 hours. He's stepping on black, dry volcano at this point. He steps, all we hear, and you see the rain and the smell comes. We look at each other, the lava's right in front of us. Okay, and it's such a beautiful thing to see.
Mesmerizing.
Oh my God, it's such a beautiful thing to see. Super hot. It's so confusing with everything that's going on. And we said, guys, it's probably a good idea for us to just turn around, to just get out of here. And that's exactly what we did. We said, let's make it. Did you find one, Rob, or not? Just play the second one right there.
Sounds like walking on an icy lake, like we hear that.
Yeah,
cracks.
exactly. Yeah. Not that one. The one below it, Rob. The one below the simulation. Right? Is that the one you clicked on? Yeah, you can put this on 2.0. This is just an example of saying when it happens, and you got to drive away.
Look at that. It's like a nuclear bomb's going off.
Seriously. Yeah. So now he's driving away. Right? And he gets bigger and bigger and bigger. And now it's chasing you. Oh my God.
It's like a Dante's Peak, right?
That's right. Dante's Peak.
Yeah. Same kind of thing.
I mean,
that's Hollywood right there.
That is Hollywood at the highest level, and you're seeing the explosives. No matter how far you get, it just keeps getting closer and closer to him. By the way, there's an image that shows if this volcano was to erupt, how far out its reach would be. Rob, can you pull up that image on the reach, what it would be? It's just worth knowing. Guys, we just want to make your day a little bit more smoother, less things to worry about. Look at this here.
Oh, I'm all right. I'm in New York. We're fine.
You're going to be all right. By the way, look at us. We barely miss it in Miami, okay, in South Florida. We are barely, Rob, that's Pompano. Pompano gets hit. We don't get hit, right? And Houston is safe. Everybody else.
What is yellow? Is that you're safe or not?
Yeah, go to see what the different things means.
Thickness in millimeters for the ash that's going to be in the atmosphere.
Ooh, okay, so you're coughing all in that region, basically. Yeah, you've got serious breathing problems.
What does blue mean, Rob? Is it telling you anything, or is it just the thickness of ash? Holy shit!
Thickness, and I believe that's millimeters.
Well,
that's
like
1
to 3.
Yeah, that's like Pompeii levels of bad day right there, right? You've got people encased in ash.
It's a bad day. It's definitely qualified as a bad day if you go through something like this. You don't want to be stuck in a thing like this.
Yeah.
What's this, Rob?
The same thing. It's just showing the impact zone if the caldera volcano erupted.
I would say don't obsess about these things, right? You can obsess about. There's so many.
No, we
threats.
want to. We want to obsess because
there's meteors, there's gamma ray bursts, there's supernovae.
Which one's worth obsessing about? Which one's worth obsessing about? Any one of these guys?
I think trying to enjoy your life's worth obsessing about.
That's what it is.
Right?
I love it.
Yeah.
What a great mentality to have. So, folks, enjoy your life. Go to Yellowstone. Take a vacation there, right? Go walk over the volcano and see what you can do with it. But let me talk to you about another thing. You ever seen the movie Interstellar?
Oh, I love that film.
Okay, so I love it as well. I remember who I watched. I don't remember where we were. We were in the most random place. We could have been in Baltimore, some weird place. We watched the movie and you leave, and you're like, let me go online. Wormhole, this. Yeah. So, well, what about this? Can we really talk? Can you really talk to dead people? I mean, is this like the PG-13 version of Ouija board? Can you go out there and do this? So, one, fiction. Two, how real is it for somebody like you?
Interstellar had a physicist, Kip Thorne, work with Chris Nolan to try and make the science as legit as they really could. So I have a lot of respect for the filmmaker because they actually, really tried hard to keep it hard science fiction, which I think is, I always enjoy that kind of stuff. Of course, the end of the movie when, he's like traveling through a black hole and then ends up somehow somewhere else. I mean, that's a little bit odd. The whole thing that love is the solution for everything. I mean, that's a bit romanticizing. There's no real physical mechanism behind any of that kind of stuff. But it made for a fantastic movie. But the stuff like, the time dilation factors, when they're on Miller's planet in that, with the ocean, where they're walking through the ocean bit. I think every 1.5 seconds, you can hear it in the movie track. It was like, do, and that was like the background bass. And every 1.5 seconds, there was a bump. And that was 1.5 seconds on the planet corresponded, I think, to 1 year back on Earth due to the time dilation effect. And so that was all figured out by Kip Thorne, that rate and the orbit and the factors and the calculations were all based off real math. So, that you can learn a lot from that movie. It's not totally on point, but it tries to take as few cheats as it can.
Okay, so let me ask you: Is there do you believe there's a possibility or the technology for one day, your mom's no longer here, your dad's no longer here? Will you be able to talk to them and have a conversation with them? You think there's a possibility?
Like reverse time travel? Yeah. I mean, I think that's probably prohibited. So, Stephen Hawking worried about this a lot. He actually held famously a party. It was in 2010, 2006, something like this. He held a party. He didn't tell anybody about it. He had a party just by himself, and it was the Time Travelers Party for time travelers to come to. He really did it. And he just sat there in this hall waiting for time travelers to come. No one came. And then it was kind of a joke. And then he advertised it after the fact. So after it happened, he said, by the way, I'm going to have a time travel party on this date, and people in the future will be able to, recognize the date, location, here it all is, and go back to that point and visit me. And of course, no one came. And, he was kind of being a bit tongue in cheek with that. I don't think it was intended as a real scientific experiment. But I think his point was like, how come we don't see any time travelers? Like, if this was a legit thing, you'd think we'd see time travelers or evidence of it by now. And so his argument was that the universe actually prohibits it because it creates paradoxes. So maybe you've heard of like the grandfather paradox, where you can go back in time, kill your granddad, and then that means that you don't exist. So if you don't exist, you can't go back and kill your granddad. So if you don't go back and kill your granddad, you do exist. And so you get this kind of cycle of illogic happening, of non-logical, non-sequitur behavior. And so he argued that because of these paradoxes, the universe just prohibits it. So it's called Hawking's chronology protection conjecture. Chronology protection conjecture. And it's a conjecture because he can't prove it. So it's not like he can write down a mathematical theorem and prove that this must be so. But he argues that the universe just really doesn't make sense if reverse time travel happens. And so whenever you think of a mechanism by which time travel might happen, the universe will always destroy it. So an instance might be wormholes, which are in Interstellar. So imagine you have two wormholes, and you can form them. There's no time travel involved. I have one here, no time travel involved. But I could always take one and accelerate it close to the speed of light and then come back to the same point. And now it would be time displaced, right? Because when you accelerate close to the speed of light, that causes time dilation. So now I do have a time machine. Whenever you have wormholes, you can always form a time machine. So now the problem is, this would seem to violate Hawking's idea, assuming these wormholes are possible in the first place. And so Hawking actually showed, and others have shown, that these things, it's kind of like having a microphone next to a loudspeaker. What happens when you do that? What do you hear? What's the sound you get?
Boom.
Yeah, you get this like feedback, right? There's like this super loud squeak. It's very horrible to hear. And the same thing will happen with these wormholes. So imagine you have a particle of light, and it will travel through one, and it will come back in time through the other. And now there's two versions of that particle. Then they both travel through. Now there's three versions. Now there's four versions. And so it's like copying itself, just like feedback with a microphone and a loudspeaker. You get a feedback effect of the particle. And before you know it, you get an infinite number of these particles collected between the two wormholes, which destabilizes the two wormholes gravitationally. And so now they both collapse. And so at the instant you form the two wormholes, they immediately collapse due to this effect. It can't, so you can, in principle, make them, but you can't have them for any length of time because they immediately collapse. So whenever you come up with an idea for a time travel machine, Hawking argues that some mechanism, and that's an example of it, the universe will screw it over for you because it's too clever to stop you from doing that.
The universe is too clever to stop you from doing that.
I mean, not literally. They're not really an agency, but...
Oh, no, I get what you're saying. I don't think it's going to be like Mossad or CIA coming in saying, hey, Rob, stop it. Don't play with time. It's against protocol. Have you ever played a Ouija board?
No.
Never have?
No.
Do you know what it is?
It's like a talking to dead people type thing, right?
Yeah.
Yeah. No, I mean, I'm not... I've actually always said, my kids often ask me about ghosts. Like, do you believe in ghosts, Dad? And I always say, look, if I detected ghosts... I would love it. I'd be excited because it would prove that when you die, there's something else afterwards. It would be incredibly scientifically interesting to know that there was something else that happens beyond the biological when you die. Of course, there's no, in my book, compelling evidence for this phenomenon, but I would always be excited by the possibility of it being true.
So you don't believe in Sam Wheat?
Sam Wheat?
Or Molly Jensen.
I don't know what those are.
You ever seen the movie Ghost with Patrick Swayze?
Oh, yeah. Are those the characters?
Yeah, Rob, you've never seen the movie Ghost? I mean, it's you can't tell me it's not real. I mean, there's Molly and there is Sam.
Proof is in the film.
This is a movie based on true story on what happened with this movie. No, I mean, listen, Ouija boards, we don't touch that kind of stuff. I remember as a kid, we had some friends that wanted to play with it. I'm like, just get that thing away from me as much as possible. Let me talk to you about another thing. Space nuclear, right? Space nuclear explosions that they do, right? I think they did one in 58 or 62. I don't know which one. It was a Starfish Prime high-altitude nuclear test conducted by U.S., a joint effort that they did this in 62. And, what is it going to do? What are the side effects are going to be? So, one, why do they do it? Two, what did we learn from actually having a nuclear test in space?
I think one of the most interesting like weaponization prospects of this thing is EMPs, so electromagnetic pulses. So when these nukes go off, they generate these electromagnetic shock waves that travel through the atmosphere and can basically short circuit electronics. By detonating it high in the atmosphere, you basically give yourself the largest range possible to hit the surface and create that effect. So I think most of the time people talk about the use of such weapons, it's not so much that you're trying to create damage on the ground through the fireball, but that you're trying to basically do a cyber attack essentially and remove all the electronic capability of the adversary.
Got it. So if the enemy has certain technology out there or satellites out there that they're watching, or they're doing what they're doing, this is my way of getting rid of their technology that the enemy is using.
Yeah, I mean, there are ways to protect against it though. So there's like a simple thing that's called like a Faraday cage, where it's like a chicken wire mesh type thing. You can even buy like wallets and bags that have this like lined in the bag. And of course you can get no cell service if you put your phone in one of these bags, because it blocks all cell phone signals or radio signals, but it protects your device from potentially an EMP. So if you're, a real doomsday and you worry about this kind of thing, you might want to put your precious electronics, maybe if you have a load of Bitcoin in a hardware wallet, for instance, that might be a good instance of like a backup. Put it in the basement and put it in one of these Faraday cage pockets or, sachets or something to protect it. So it's it can be like all weapons, there's always a way around it, so this isn't a foolproof way, but it would be pretty damaging to the infrastructure if somebody detonates one of these things.
What are you most excited about? Like with all the projects that you're working on, what are you most excited about?
I've just recently got tenure at Columbia. So now...
Congrats.
Yeah, thank you. And I think one of the objectives of tenure is that it gives you the freedom to really just go for like whatever you want. Like just take the gloves off and find the things that you're really passionate about and don't worry so much about grants. And the things we've been talking about, like looking for alien life in the universe, have fascinated me for a long time. And I've written papers on that topic. But I really want to push harder on that, and also how to get to the stars. We have a project in my team right now. I'm not going to talk about it too much because it's still kind of top secret, but we do have it's kind of ridiculous to say out loud, but an interstellar propulsion system that we're designing in my team. And that's the kind of thing that I would never do unless I was tenured. But me and a couple of engineering students have been working on this project for the last year or two. And we think we have something interesting to contribute to that idea. I don't know if it will work out. I'm an astrophysicist, not an engineer, but we have an interesting design that nobody's ever thought of that we think could be better than some of the alternatives that people propose, like the Starshot thing we've talked about so far. So that's the kind of stuff I get buzzed about is, I had this dream as a kid, looking up at the stars, wondering who else was out there and wanting to touch the stars. And I want to do whatever I can in my life to try to advance humanity's mission to try and achieve that. I think I'm not going to solve it. I'm one person, but maybe I can add a small piece to the puzzle and we'll get there together.
I love it. You seem very sincere about it. I've enjoyed listening to you. This has actually been a very interesting podcast. I am going to lobby for you to be able to raise $250 billion so we can find out what the hell is going on out there with this technology. I'm surprised other people haven't brought it up yet, because if a president like John F. Kennedy was to sell a vision like that, I think a lot of people would buy into it. And if we really are concerned about the future, this could be one way that we can find out for a fact what's really taking place. Yeah. By the way, if there's anything you would want people to go look at, would it be mainly your YouTube channel, or is there a website or a project that you want them to look at?
Yeah, so you can check out my YouTube channel. That's Cool Worlds Lab, at Cool Worlds Lab on YouTube. We also have the Cool Worlds podcast, so just at Cool Worlds Podcast. And there I'm mostly interviewing scientists and astronomers, physicists, thinkers about our place in the universe. And then on top of that, there's the website coolworldslab.com, where we have kind of a unique funding model for my team. So we do the usual thing of applying for NASA grants and federal grants, things like this. But we also get a lot of people who just donate money to my team out of their own pocket. It could be as much of a price of a coffee per month that they're giving. So if you hit support at the top of this page, you can become a donor to my research lab, the Cool Worlds team. And through these donations, we can do stuff that you can't do through conventional federal funding. So like the interstellar propulsion system, there's no way I can write to NASA and say, give me, $100,000 to start working on just a preliminary idea for this, just to get the ball rolling. They're just going to laugh you out the room. But thanks to, support from people who have a bit of vision.
That is so cool.
This is worth maybe investing in.
The Illuminati.
The Illuminati right at the top there, yeah. Those are our top donors. And this money goes, through to Columbia. It doesn't go into my pocket. I think that's the advantage of this. This is tax deductible. I don't see this money. It's all used for research, purely research money. So you have this is not like a Patreon where, people are using this for salary. This is just research funds.
That's cool.
So if you want to support real research, this is the way to do it.
Rob, let's put this link below in the description and the chat for people to go check out and support. And again, I've enjoyed spending this time with you, man. I appreciate you coming out. Thank you so much, man. This was great. Thank you.
In these uncertain times, if there's anything we need people to believe the future looks bright. So if you've heard about me saying this mission to you, we're on a mission to get 1 million people to wear this gear. And this is what we're doing. If you buy one of these hats, there's a category of buying one hat, getting the second one free. If you haven't yet worn this gear publicly, go ahead and test it out. Buy some of the gear, wear it in public, and see how many people will stop by and say, you also watch Valuetainment? You also follow PBD Podcast? I do too. Place your order. Go to vtmerch.com, click on the link above or below, place your order, and represent the VT and the PBD Podcast gear.